Warning, the video you're about to watch contains mathematics at the level of college algebra and trigonometry. All material has an assumed prerequisite of both Algebra 1, which is elementary algebra, and Algebra 2, which is intermediate algebra. While some prerequisite topics are reviewed briefly, a more thorough review of these entrance topics can be found by searching the web.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes.
Hello, my name is Roy Simpson, Professor of Mathematics at Cosumnes River College in Sacramento, California. This is yet another video in a series on vectors for trigonometry and pre-calculus. And if you're in, let's say, Calc 2, it's probably a good video to watch as well, or maybe Calc 3. In this video, we're going to talk about unit vectors and the component form of vectors. You should already have watched my videos on a geometric approach to vectors and an algebraic approach to vectors, and then vector arithmetic and properties of vectors. So all that should be done. And now we're going to start with unit vectors. The vectors, that's supposed to be an I, but for some reason it doesn't look like one to me, but that's I. The vector I is defined to be 1, 0. And the vector j is defined to be 0, 1. And those together are called the unit vectors for two-dimensional space. If you draw them out, 1, 0 looks like this. That's the vector I. See, I can't even draw it. I. There we go. And the vector j is the unit vector in the vertical direction, is a good way to think about it. From these two vectors, you can actually recreate any vector in two-dimensional space. And the unit vectors actually carry over to three-dimensional, four-dimensional, and n-dimensional space. So you can have unit vectors for any type of space. So let's practice here. Here's our good old vector v, which is equal to -3, 1. We want to write this in terms of the unit vectors. And here's the way you could do that. V is equal to, well, I'll start this way. It's -3, 1, but you can actually dice that apart. That's -3, 0 plus 0, 1, which is the same thing as, I'm going to zoom in because my handwriting sucks that far out. So I'm going to zoom in there, and I'm going to say that's the same thing as -3 times the vector 1, 0 plus the vector 0, 1. But the vector 1, 0, that's the vector I. And the vector 0, 1, that's the vector j. And there you have it. V has been written in terms of the unit vectors. This is a very nice way to write vectors in terms of the unit vectors for future math courses. All the arithmetic that we had previously done still holds for the unit vectors. So computing 2 times I is the same thing as saying what's 2 times 1, 0, which is the same as 2, 0. And this guy right here, 3i minus 2j, is the same thing as 3 times 1, 0 minus 2 times 0, 1. Or in other words, I'll just write it down below, 3, 0 plus 0, -2. Or in other words, 3, -2. Now, nobody would ever really take that much time doing it. So if somebody came to you and said, hey, I need to know what -7i plus 3/2 j looks like, you could say, well, that's just -7, 3/2. The coefficient on I gives you the first component. The coefficient on j gives you the second component. That's all. Now we're getting into the nitty-gritty of vectors. So we got all the basic stuff down, but now we're going to get into kind of the beginning. We're going to open the door to applications. So the direction of a vector v is the smallest positive, that's critical, smallest positive angle in standard position formed by the positive x-axis and v, which basically means a vector could have a direction all the way up to 360 degrees, not including 360. So anything between 0 and 360. For example, let's find the direction of these two, again, friendly vectors we've been working with this entire time. The first one I'm going to skip. I'm going to do the second one, which is the vector u there, because that's a little bit easier to see initially. So the vector u from a very basic standpoint, is pretty easy to understand what angle it makes, right? Because it goes over 5 and up 5. You guys should already know 45 degrees is going to be the direction of vector u. So vector u has a 45 degree angle. You could also answer in radians. With vectors, though, you're likely going to use degrees more than radians because vectors are going to be used in physics and in engineering. So my guess is, for the most part, you're going to be working with degrees. But what if the vector is not as simple as 5, 5, but instead is some weird vector like -3, 1? Well, still not too bad. The way that I would go about doing this, and therefore the way you should go about doing this, is recall that trigonometry is about reference angles and quadrants. So I'd love to know the quadrant into which the vector v points. So here is the vector v in standard position. It goes back 1, 2, 3, and up 1. So it looks like this. So it points into quadrant 2. Remember, trig is about reference angles and quadrants. I just need to know what is the reference angle here, theta hat. Well, let's see. Theta. If I told you went back 3 units and then up 1, you could easily see that I've just drawn a right triangle, and I can get a reference angle off that right triangle by using a tangent inverse. So the arctan is what I'm going to use here. And remember, when you're using the arctangent for anything, you should do that using the positive values, not these negative values, but 1 over 3, not 1 over -3, because you're trying to get a reference angle. You can use the quadrant and the reference angle to find the actual angle, but to do so, you're going to need to use the positive values here. Now, I just have a calculator nearby. I'm going to compute this out in degrees, and that's roughly 18.4 degrees. So I have a reference angle of 18.4 degrees in quadrant 2. That means the actual angle for V is going to roughly be 180 minus that, and 180 minus that is 161.6. 161.6 degrees. Let me just double check that. 162. Yep, that's exactly what it is. So there you go. That's how you find the direction of a vector. Pretty easy, right? Usually you'll be using, in fact, always you'll be using the tangent inverse. And then look at where that vector is pointing to tell you the quadrant. Tangent inverse will give you the reference angle, and the vector itself will give you the quadrant, and you'll be ready to go. And this naturally leads to the components of a vector, the horizontal and vertical components of a vector. We already know if somebody hands us a vector, v, which is a comma b, the horizontal component is a and the vertical component is b. We know that. We also know we could write that as a times the unit vector I plus b times the unit vector j. We totally know that too. However, what if somebody just gives us the values of a and b and an angle? Or better yet, what if they give us the angle and the size of the vector v? Could we rebuild what the vector actually is? And the answer is yes. The horizontal component a is equal to the magnitude of the vector v times the cosine of theta. And the vertical component b is the magnitude of the vector v times the sine of theta. That is, the vector itself can be written, since we have it right up here, as ai plus b times the vector j. You could rewrite it this way if you wanted to. You don't actually have to write it this way, but some people prefer that. I don't, honestly. But I do want to showcase how easy it is to prove this. Incredibly easy, in fact. Suppose you're given a vector, and when I say prove, I'm not going to be super rigorous here, because generally speaking, you're coming across this at the end of your semester, your brain is wasted, so let's just get a visual proof of this. You have a vector v, here it is, right here, and that vector v is equal to some component a, some vertical component b. That is, you have some distance horizontally and some distance vertically, and that vertical distance we would call B, and that horizontal distance we would call A. And you know that the angle that the vector makes with the positive x-axis we call theta. Whether this was pointed in quadrant 1 or 2 or 3 or 4, doesn't matter, the proof is the same. I just like this proof in quadrant 1. Well, if somebody said, I don't know what this A is, could we please compute it? I would say, yeah. What trig function relates this angle with that side A with the hypotenuse? Now you may say, I don't have the length of that hypotenuse. That hypotenuse is not the vector v, it's the magnitude of the vector v. And I would say, yep, you're right. You're absolutely right. But you could still say it's the magnitude of the vector v. So cosine of theta would equal A over the magnitude of the vector v. That is, A is equal to the magnitude of the vector v times the cosine of theta. And that is actually the proof for the horizontal component. There you go. It's right there. And the vertical component's the same thing, right? The sine of theta is going to be B over the magnitude of the vector, or the length of the vector. Therefore, B is equal to the length of the vector times the sine of theta. And that's it. Proof done. Very fast. So let's go ahead and use this. And I have both situations where you're going to use this here. Find the horizontal and vertical components of the vector with length 40 and direction 210 degrees. And write the vector in terms of the unit vector. All right. Well, you could draw this out without remembering the theorem. You could still figure out what the theorem is just by drawing a picture. I have a vector that makes an angle of 210 degrees and goes out a length of 40. And I want to know what is the horizontal component and what is the vertical component, because that would be those would be the components of the vector. Well, I would find the reference angle and the quadrant, because trig is about reference angles and quadrants. You can easily see it's quadrant 3, and we know with 210 degrees, the reference angle, theta hat, is 30 degrees. So I'm going to go ahead and draw a 30, 60, 90 triangle, 30, 60, 90, or you could just use sines and cosines if you want. Doesn't matter, honestly. It's 1, 2, root 3. I just like to kick it old school, bring it back, right? And we know our hypotenuse is of length 40. So if you multiply all three sides by 20, you get the hypotenuse of length 40. You'll get the side adjacent to 30 degrees to be 20 root 3, and the side opposite 30 degrees to be 20 times 1. That is, the side adjacent to this 30 degree angle right here is going to be 20 root 3, but it's negative. And the side opposite will be 20, but again, it's negative because we're in quadrant 3. And so our vector in component form, or I suppose in vector form, is x equals negative 20 root 3, y is equal to a negative 20. But if you want to write this in unit vector form, it would be negative 20 root 3 times the I vector minus 20 times the j vector. You could also do this problem very, very easily just using sines and cosines. You could have said, well, I don't know what a and b are, but I know that for example, cosine of 30 degrees would give me a over 40, or in other words, a must be 40 times the cosine of 30 degrees. That's actually not true in this case, because that would give you a positive value. However, you know it's negative in quadrant 3, so you could go ahead and stack a negative on there. Or you could memorize that theorem we wrote down a moment ago, and instead of using the reference angle, you could have just said, oh, well, a is just the magnitude of the vector times cosine of 210 degrees. And when you do that, you'll get a negative 20 root 3. And B is going to be, again, 40 times the sine of 210 degrees. And when you do that, oops, that's supposed to be 210. And when you do that, you get a negative 20. So there's a lot of ways you can do this mathematics now, which is really nice. You have options. But we've answered the question earlier, so no need to go any further with this. But it's nice to know you have a lot of options when you do these styles of problems. Now here's the opposite question. Here's a vector, and we're asked to find the magnitude and the direction. And actually this one we already found the direction. However, let's just do it again to kind of get used to it. So I'll start with the direction. The vector v is given, so I'm not even going to bother with that, but I'll say our reference angle is going to be the tangent inverse of the absolute value of y over the absolute value of the x. And I think when we computed that earlier, I think it was 18 point, I have to grab my calculator actually because I forget what it was. And I'm too lazy to go back. So it's 18.4 degrees. All right. And if you notice, we have a quadrant 2 vector. So our actual angle, whoops, that's supposed to be a theta, for the vector v, is going to be 161.6 degrees. And 162, yep. And now finding the magnitude we've actually computed previously as well. That's just going to be the square root of 3 squared plus 1 squared over root 10. So there you go. You can be asked all these different kinds of questions. You should be able to answer them because they're not too terribly difficult. Now the next video, we'll get into some challenging stuff because that's the applications, but that's also where vectors sing. That's where they do the best job they can do, and that's where they're most entertaining.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes obstacles getting in our way, cause affects more than we can sometimes see. Things for what they are and work together until you feel at peace. Just listen close, don't talk too much that isn't kosher. You may really hurt inside. It doesn't justify you to speak too loud and cry.